Hello, this is Dr. Schleith, and in this video I'll show you how to theoretically calculate the coefficient of friction, and we'll be able to take a quick measurement in the lab with a quick calculation to check our conclusion for the coefficient of friction, which we're going to get from our other lab this week. So the lab work this week involves pulling a block along a level horizontal surface so that it moves with constant velocity. By moving at constant velocity, we're ensuring that the force that we pull with, which we can measure, will equal the force of friction acting against it. And to make the lab even stronger, we're going to actually vary the weight of the block and therefore vary the normal force that sort of matches the weight, because theory suggests that the force of friction is equal to the coefficient of friction times the normal force, where the coefficient of friction is just a number that sort of says how slick or slippery or rough the surfaces are. The bigger the the bigger this number is, the greater force would be required to move the object, or the greater the frictional force is, the higher this number is. All right, so how can we determine the coefficient of friction theoretically? What we're going to do is consider the case where we put the block on an inclined plane, and we can increase the angle theta here until enough of the weight of the block acts down the ramp so that it starts to slide. So as we increase this angle, there's going to be enough friction to keep the block stationary, but there will be a point, and we'll call that point where theta is at the critical angle, which is the angle just when the block's component of weight down the ramp causes it to accelerate and causes it to move down the ramp. All right, so that's going to be the critical angle. And this is going to be the thing that we can measure in the lab. So our procedure would be to place our block on the ramp and increase the angle until we observe the block starts to slide down. And the moment that it does, we'll measure the angle that the ramp is making relative to the horizontal. But how will that angle give us the coefficient of friction? Well, let's see. We'll start by drawing some vectors here. So here we have the weight of the block, and it's equal to m times g. We know that there's a normal force that acts perpendicular to the ramp surface, and so there's a component of weight that acts into the ramp this way. So if this angle here is theta, then this angle here is also theta, because I've got a triangle here where I've got a 90-degree angle and an angle theta. So if we just assume that, this is 90 and this is, let's say, 10 degrees, so we'd have 100 degrees there. Well, then we know that this angle here must be the remaining 80 degrees for our 180-degree triangle. And so if this is 80 degrees, but I've got another right triangle right here, and this much of it is 80, well, then there's my 10, which would be equal to this one. So you can kind of, prove to yourself that whatever angle we have here, as long as we draw this line perpendicular to the surface, and then this one, this one is perpendicular to the horizontal, and this one is perpendicular to the ramp, then this angle will always equal this angle. So here we have a component of weight that's going into the ramp, and I'll call that the y component of weight. And so there is a component of weight which acts down the ramp right there, and it's opposite the angle. I'm going to translate that vector and show it sort of right here. So there's a component of weight, the x component of weight, which acts down the ramp. And that component of weight is counteracted by the frictional force. We're considering the point right when the component of weight becomes equal to the frictional force or just a little bit greater than it, and that's what causes the block to start to accelerate, because there will be a net force in the direction down the ramp, and that's when the block's gonna slide right at the critical angle. All right, now let's see what we've got here. In the y direction, let's apply Newton's second law. So the sum of the forces in the y direction is equal to mass times the acceleration in the y direction. And the mass is going to be the mass of our block here. So what forces do we have in the y direction? Well, we've got the normal force, and then opposing it, we've got the y component of weight, and that equals mass times the acceleration in the y direction. Now remember that the y component of weight is adjacent to this angle theta here, and so we can write it as the cosine theta times the weight, which is mg. So the y component is really mg cosine theta. Because the object is not accelerating in the y direction, we know that the right side of this equation is 0, and so the normal force minus the y component of weight is 0, or the normal force is equal to the y component of weight. And the y component of weight is mg cosine theta. The x component of weight, which is opposite this angle, right? So here in our vector triangle where weight is the hypotenuse, I can see that the x component, if I'm calling sort of the direction down the ramp positive x, then the x component of weight here would be equal to the sine of theta times mg, right? That's the x component of weight. So x component of weight is mg sine theta. So now by considering summing the forces in the x direction, applying Newton's second law in the x direction, I could say the sum of the forces in the x direction equals mass times the acceleration in the x direction. And I'm still going to consider the point right at the critical angle, right when the two are equal. So sort of just before the block starts to slide down, because the x component of weight has sort of overwhelmed the frictional force. So I have the x forces are the x component of weight in one direction, and then opposing that is the frictional force. And that's going to equal 0 because, again, we're going to consider sort of the point right when the two forces are balanced, just before the x component of weight sort of overwhelms and it starts to slide down. So here we can see that the x component of weight, which is mg sine theta, would be equal to the force of friction, right, by adding the force of friction to both sides. From our lab work, theory suggests that the force of friction is equal to mu times the normal force. And so we can make a substitution here. Mg sine theta, which is equal to the frictional force, but the frictional force is equal to mu times the normal force, right, from this equation. And by considering the y direction, we know that the normal force is equal to mg cosine theta. So we can write mg sine theta equals mu times the normal force, which is mg cosine theta. Now, by dividing each side by mg cosine theta, we can see that mu, the coefficient of friction, would equal mg sine theta divided by mg cosine theta. So it doesn't matter the mass or the gravity field strength. The coefficient of friction is really just about the surfaces, sort of how rough or smooth they are. And so by measuring the critical angle and by simplifying this one step further, we know that the sine over the cosine is the tangent. We can see that the coefficient of friction should be equal to the tangent of the critical angle that we can measure in the lab. So once we've completed this lab work, where we're plotting a graph of the force of friction against the normal force so that the best fit line will equal the coefficient of friction, the slope of the best fit line will equal the coefficient of friction, we can then do a quick measurement of the critical angle by inclining our ramp, observing the moment the block starts to slide down, and using a protractor to measure the critical angle. And by taking the tangent of that critical angle, we should also be determining the same coefficient of friction that we get from the slope of our best fit line.